This is the second video in our unit dealing with solutions. And today we're going to talk about actually two different things. One of the things we're going to talk about is we're going to talk about how to create a solution. And then we're also going to talk about combining solutions with stoichiometry and how we can do both of those things at the same time. So our goal today is to be able to describe the steps to create a solution of a certain molarity, and then we're going to use molarity and volume to solve problems using our good friend stoichiometry. So when we talk about a solution, there's a lot of things that we know based on the information that is provided to us. For example, let's think of in real life. If I were to ask you to make some Kool-Aid, you wouldn't just say, oh, okay, I'll go make you some Kool-Aid. You might think, okay, what other information do I need to know in order to make that Kool-Aid? So some of the questions that you might ask in order to make the Kool-Aid might be, how strong do you want the flavor to be? Some people like it a little bit stronger. Some people might like it a little bit weaker. Someone might ask, do you like it really sweet? Basically, how much sugar do I need to add? Other than flavoring, there's also the sweetness factor. How much sugar should I add? And then even the question of how much. Do you want 2 quarts? Do you want a gallon? Is it for a big party? Do you need a whole bunch? There's a lot of questions that you might ask when creating a solution of Kool-Aid. Well, in chemistry, it's the same thing. When we're going to do a lab and I need a solution, there are certain questions that the lab tech asks me, and I need to make sure that I'm providing that information. So I don't just say I need some hydrochloric acid. I tell her how much I need. I tell her how strong it needs to be, and so forth. So if I were to ask you to make a solution of sodium chloride, you would need to know a few things. You would certainly want to know what concentration do you want that solution to be. And remember, when we talk about concentration, we're talking about molarity. So when we talk about molarity, remember that molarity is equal to the moles of the solute divided by the volume measured in liters of the solution. So it's the moles of the solute divided by the liters of the solution. And then you're also going to want to know how much of that solution do you need. So again, I'm not just going to say make some sodium chloride. I'm going to say I need 2 liters of whatever concentration of sodium chloride I need. So let's look at the example right here. So when you're asked to create a solution, the above information must be given to you, or it must be given in a way that you can find it. So if I were to say to you, describe the steps necessary to create 700 milliliters of a 1.25 molar sodium chloride solution. And obviously I would provide you with the sodium chloride, I would provide you with a balance, I would provide you with all the things that you would need. So here it is again. In order to create this solution above, we need to know how much sodium chloride we're going to need. Now, in order to do that, we have to be able to use grams. We do not know, we can't measure on a balance the number of moles that we need. And remember that if we're creating a molar solution, we do need to know the moles of the solute. So what we need to be able to do is we need to take our molarity and we need to figure out the molarity and the volume to figure out how many moles we're going to need. So we're going to start with our 1.25 molar, and remember that means moles over liters. And then what we need to do to that is basically what we're trying to get is we're trying to get moles of sodium chloride. So the first thing we're going to do is we're going to take our molarity and we're going to multiply it by the volume of our solution. Now this is liters down here, so our volume here also has to be in liters. So I'm going to move my decimal point 3 spaces to the left. That makes it 0.750 liters, and that is going to equal 1.25 times 0.75, which is equal to 0.938 moles of NaCl. So when you're given the concentration of a solution and you're given the volume of the solution, you know that you can always use those 2 pieces of information to find the moles of that solute. Remember that this part up here on the top is the moles of the solute. The solute is what is dissolving in the water. So this is how many moles of NaCl we have to be able to use to make this solution. So now what we can do is we're going to take our 0.938 moles of NaCl. Now again, we need to know how many grams of NaCl we're going to need. So I'm taking my 0.938 moles of NaCl and I'm going to go to the periodic table. I know I need to cancel moles, so I'm going to put 1 mole on the bottom, and I'm going to put the molar mass of sodium chloride on the top. So that is 58.5 grams. Sodium is 23, chlorine is 35.5. That adds up to 58.5. So then I take 0.938 times 58.5, and that equals, again, rounded to 3 significant digits here, 54.9 grams of NaCl. Okay, so now I know. That was my math part. That's my quantitative part of solution, of solving this solution, is what mass of sodium chloride am I going to need for this solution. So once we figured out how much NaCl we're going to need, 54.9, let's write this up here again. Now we can create the solution in just a few steps. Okay, so step number 1, I might say add 54.9 grams of NaCl to a and let's see, how much of it did we need? We need 750 milliliters of it, to a 750 milliliter, now this might be a new word for you, volumetric flask. And a volumetric flask is a flask that only measures one amount. And what it looks like is, let me come back here and erase this screen. What it looks like is it's kind of got a little circle at the top for the opening, then it comes down like this, and then it comes down and around like this, and there'll be one line on it right here, and that line is the amount that, in this case, what we're looking for. So it might be a 500 milliliter volumetric flask. If it's 500, then this line right here will say 500 milliliters. If it's a 1 liter volumetric flask, that'll be a liter. In this case, we want it to be a 750 milliliter volumetric flask. So we're going to just assume that that line right there is going to be the 750 milliliter mark. So we're going to add 54.9 grams of sodium chloride to a 750 milliliter volumetric flask. Step number 2, we're going to add water until 750 milliliters of solution is reached. Now you'll notice that I did not say that we add 750 milliliters of water, because remember, some of this sodium chloride is going to take up some of that space. And the key here is that just understanding that we really don't know exactly how much water we're going to add. We're going to continue to add water until our entire solution, the water and the sodium chloride, adds up to 750 milliliters. So remember that when we're dealing with molarity, we're dealing with the volume of the solution, which includes that sodium chloride in it. So, in terms of how much water do you actually add, you don't know. You add enough until you reach 750 milliliters. And so if you do this, if you add 54.9 grams of sodium chloride, and then you add water until you reach 750 milliliters, what have you created? You've created 750 milliliters of a 1.25 molar sodium chloride solution. Okay, now, in our previous example, what I showed you is I showed you a way that you can use the molarity and the volume to get moles. That's a very useful piece of information because just like when we learned about stoichiometry, here it is again. When we learned about stoichiometry, many times when we measure the amount of a substance is we measured it in grams. Well, now when we're dealing with solution stoichiometry, instead of measuring things in grams, we're measuring them in volume and in concentration. And so when we did stoichiometry, if I gave you something in grams, the first thing you had to do is you had to convert to moles. And the way that you did that is you used the molar mass from the periodic table. And then you could get moles of whatever that substance was. I'm just going to call it A. And then you would use the balanced equation to go from moles of A to moles of something else. Let's just call it B. And that right there, that was our stoichiometry step. Well, now that we're dealing with solutions, instead of converting grams to moles, what we can do is we can use the molarity and the volume, and we can multiply them together, just like how I just did in the previous example, and we can find the moles of the solute that way. Then, once we have moles of whatever it is, then we can do stoichiometry problems to find out our answer. So, let's start with a simple one. First one says, how many moles of sodium sulfate are there in 250 milliliters of a 0.5 molar solution? So, let's take a look here. If it's a 0.5 molar solution, it's 0.500, and again, you can leave it as a big M. A lot of times I write it as moles per liter. It means the same thing. And I'm going to multiply by the volume of the solution, 0.250. Notice I converted my milliliters to liters. So I'm going to take 0.500 times it by 0.250, and I'm going to get an answer of 0.125 moles of Na2SO4. Now, so this is actually very similar to what we did in the past, where we converted our grams to moles. This is the beginning of the problem, because now, once we have our moles of sodium sulfate, there's lots of different things we can do with that. With moles, you've got a lot of different things you can do. So, for example, let's use that same amount, let's use that same concentration, and that same volume. And we know, let's come back here real quick. We know that we've got 0.125 moles of Na2SO4. So here's a question that you might see involving that. It says, what mass of sodium chloride is created from 250 milliliters of a 0.5 molar solution of Na2SO4 to which excess, notice that word right there, we should be familiar with that, excess ammonium chloride is added. Okay, so in this case, we need to have a balanced equation. And so in order to have a balanced equation, we have to look, okay, NaCl, or excuse me, not sodium chloride is being created, excuse me, let me start that one over. So we've got sodium sulfate, Na2SO4, is added to excess ammonium chloride. Ammonium is NH4Cl. And then one of the products it tells us is sodium chloride. So we can see that the Na is going to go with the Cl. And so what's our other product going to be? Hopefully you recognize this as a double replacement reaction where the NH4 is going to go with the SO4. And so that sodium or ammonium, excuse me, is +1. Sulfate has a -2 charge. And I don't have enough space here to write it, so I'm going to write it down here. NH4 parentheses 2 SO4. Okay, and now we want to balance that equation. So I see 2 sodiums here to start with. I see 1 sodium over here, so I'm going to put a 2 right there. That makes 2 chlorines, so I'm going to put a 2 right there. And that balances out our ammoniums. We've got 2 ammoniums down there. So now remember, from our previous step, we had 0.125 moles of Na2SO4. And now they want to know what mass of sodium chloride is created. So that we're starting with our moles of this, and we need to get to grams of this. So calculate the number moles of sodium sulfate that we have. We already did. It's 0.125 moles, unless I changed the number. I didn't pay attention, but I didn't. It's still those same numbers from the previous example. So we've got 0.125 moles of sodium sulfate. So that's Na2SO4. Now we're going to use stoichiometry to convert the moles of sodium sulfate to grams of sodium chloride. So we're going to go 0.125 moles of Na2SO4. And I want to cancel moles of Na2SO4. So I'm going to put moles of Na2SO4 on the bottom and moles of whatever they're asking me about, sodium chloride, on the top. I'm going to go back to my balanced equation here. 1 mole of Na2SO4 is going to produce 2 moles of sodium chloride. So 1 mole of Na2SO4, 2 moles of sodium chloride. And then I'm going to cancel my moles of Na2SO4. 1.25 times 2 equals 0.250 moles of NaCl. Okay, now, unfortunately, I skipped this part. Oh, no, I didn't. It says 2 grams of sodium chloride. So, you know what? Let's go ahead and we're going to take out that last step right there, right here. Now, so instead of stopping here, now we can go 1 mole of NaCl has a mass of 58.5 grams. Again, that number right there comes from the periodic table. So now I'm going to take my calculator. I'm going to go 0.125 times 2 times 58.5, which I get an answer of 14.6 grams of sodium chloride. And that is my final answer. So the first thing we have to do is we have to use the concentration and the volume to convert to moles of whatever our solute is. We then use our stoichiometry step using the balanced equation, and then we can convert to grams based on the mass of our final product. Okay, so here's another example of this. I want you to go ahead and pause the video at this time and see if you can figure it out. Let's read it together here and then we'll pause it. 0.0457 liters of 0.5 molar sulfuric acid is required to completely react with 0.20 liters of sodium hydroxide. What is the concentration of the sodium hydroxide solution? So if you would at this point, I'll tell you right now, you need a balanced equation and you're going to do something very similar to what we just did. So go ahead and pause the video at this time and then we will continue once you've gotten as far as you can get. All right, so the first thing I'm going to do is I'm going to write a balanced equation. H2SO4 plus NaOH is going to produce, this is an acid, this is a base. When you combine an acid and a base together, you always get water. Notice the H and the OH, those go together to make water. And then what's left is the sodium and the sulfate. So we're going to have Na2SO4. And then to balance that, we're going to need a 2 here for the sodiums, and then a 2 here to balance out the hydrogens and the oxygens. Okay, so we've got our balanced equation. Now, if we notice here, they want to know the concentration of the sodium hydroxide. When they say concentration, they mean molarity, so that means moles of solute over liters of solution. We already have the liters of our solution right here. All that we really need to do is we need to figure out the moles of the solute of the sodium hydroxide, and that will get us the moles that we need to get the concentration. So, if you're not sure what to do, the first thing you always do is, like I talked about earlier, if they give you the concentration and they give you the volume, the first thing you do with that is you always convert to moles. So we're going to take our 500 moles per liter, and we're going to multiply by the volume, 0.0457 liters, and we're going to get an answer. So 0.500 times 0.0457 is equal to 0.0229 moles of H2SO4. And then using that information, now we can do our stoichiometry step. We can go 0.0229 moles of H2SO4. And now using the balanced equation, we're going to say 1 mole of H2SO4 is going to be required to react with 2 moles of NaOH. So I'm going to take that answer, 0.0229, I'm going to times it by 0.0229, timesing it by 2, and that equals 0.0458 moles of NaOH. And so now, it's like we said earlier, now since we already have the volume, and now we've got the moles, we can just put those two things together and we can get our concentration. So let's get rid of some of this so we can have a little bit of room here. So I'm going to take my moles that I just found down here in the corner, and I'm going to switch back to the pen here. 0.0458 moles divided by 0.020 liters. So divided by 0.020 liters equals 2.29 big M, or moles per liter, however you would like to write it. Okay, and that is our final answer. So you'll notice that both questions were somewhat similar. I did ask you questions a little bit differently in each one, but again, the key is understanding that when they give you volume and they give you the concentration, you've got to use that information to get moles. Once you have moles, then you have a lot of possibilities on what you can find, especially when you use stoichiometry. Okay, here's one more example, and then we're done with this slideshow. So we're going to write a balanced equation. So 70.5 grams of potassium phosphate. So potassium phosphate. Now again, I would ask you at this point to go ahead and pause the video. Try to do as much of this as you can. If not, do the whole thing, and then come back and see where we're at. So 70.5 grams of potassium phosphate. So potassium phosphate to me is K3PO4 is added to 15 milliliters of silver nitrate. And silver always has a charge of +1, so that's going to be AgNO3. Forming potassium nitrate, so this is just a double replacement reaction, KNO3 plus Ag3PO4. Now in terms of balancing, I think we need a 3 here, and we need a 3 here, and now it is balanced. Okay, second part of this question asks, what's the limiting reactant? So notice in the previous example, I used that word excess. That means we don't need to figure out what the limiting reactant is, but notice here I gave you the amount of one reactant, and I gave you a concentration and a volume of another reactant. That means we don't know which one's going to run out first. We have to do some math to figure that out. So it doesn't matter which one we start with. Let's start with our 0.050 moles per liter of silver nitrate. We're going to times it by 15 liters, and that's going to get us moles of silver nitrate. So instead of getting my answer, what I'm going to do is I'm going to try to do it a little bit quicker this time. We know that this is moles of AgNO3. So I'm just going to continue. I'm going to put moles of AgNO3 on the bottom. And I'm going to put moles of my other reactant, potassium phosphate, on the top. And then from my balanced equation, 3 moles of silver nitrate reacts with 1 mole of potassium phosphate. So again, very similar to what I would do when I did regular stoichiometry. I would convert my grams to moles, and then I would go moles to moles using the balanced equation. Here I use my concentration and my volume to get moles of silver nitrate instead of converting grams to moles. And now I can convert 1 mole of K3PO4, and now I need the molar mass of potassium phosphate. Okay, so the molar mass of potassium is 39.1. Multiply that times 3, plus 31 for phosphorus, and then 64 for the oxygen, equals 212.3 grams. So now I'm going to take my initial numbers. Listen to how I do the math here. I'm going to start at the very beginning, 0.050 times 15 divided by 3 times 212.3 equals 53.1 grams of potassium phosphate. And so now we need to compare. This is how much I need. I need 53.1 grams of potassium phosphate. I actually have 70.5 grams of potassium phosphate. And so I have a lot more than what I actually need. And so now, since I know that potassium phosphate is extra, I know that my silver nitrate is going to be my limiting reactant. So now I can go to my final question. What mass of silver nitrate, that should say silver phosphate, sorry about that. What mass of silver phosphate is going to be formed? So I'm going to use my limiting reactant, which again is this silver nitrate. So I'm going to take 0.050 molarity, or moles per liter, times the concentration, or times the volume, 15 liters. And again, that's moles of AgNO3. My volumes cancel. And so now I'm going to go from moles of AgNO3 to moles of what I'm asking you for, silver phosphate, which is Ag3PO4. And according to my balanced equation, 3 moles of silver nitrate are going to react with 1 mole of silver phosphate. So now I've got moles of silver phosphate, and now my last step, I'm going to continue down here, times 1 mole of silver phosphate is going to have a mass of 107.9 is the molar mass of silver. I'm going to times that by 3, plus my 31, plus my 64 from the oxygens, equals 418.7 grams. So again, let's check our math here. 0.050 times 15 divided by 3 times 418.7 equals 105 grams of Ag3PO4. And that is our final answer. So hopefully you got that. Let's go ahead and move on to the problems dealing with creating solutions and solution stoichiometry.